like American Institute of Physics, elsewhere, Springer, such a reputed journals. Now, in this event, I would request to Honorable Vice Principal of our college, Dr. V.P. Chaudhary sir, please inaugurate this event with your good wishes. Our Vice Principal is a source of motivation and he always encourages us to organize such type of event. So please share your views, sir. Dr. V.P. Chaudhary sir.
First of all, I congratulate Dr. More, the head of the department, for conducting such academic activities. Secondly, I am very much thankful to him for giving me an opportunity to share my views in this webinar. Thirdly, I, being the part of the administrative office, welcome Honorable Dr. Rajnish Baikar from Pune, who is going to address to the students on application of mathematics. So instead of taking much more time of the listener and the speaker, I give my best wishes to the webinar. Thanks a lot, sir. Thank you, sir. Thanks a lot.
Thank you, sir. Now, I would like to request to our resource person, Honorable Dr. Sri Rajnish Malekar sir, please give your valuable guidance to our student so that they will motivate and will do the career in mathematics. So once again, I would like to request to Dr. Rajnish Malekar sir, please guide us.
Okay, thank you, More sir. Am I audible?
Yes, sir. Yes, sir.
Okay, thank you. Thank you, More sir. Thank you, Chaudhary sir, for inviting me to this talk. And it's really been nice to with the students of regular colleges as we teach to the students of National Defence Academy who are at a different level. So while discussing with Dr. More sir, what I came to know was the enrolling for mathematics subject as such, I think in your college or as such maybe the rural colleges in Maharashtra, it's quite low, which actually is quite surprising in these days, as now the mathematics has been used in so much applications, and recently all these data sciences and artificial intelligence, the basic requirement is mathematics. So there are very simple mathematics that is being used to actually study these subjects. So in fact, I'll suggest all of you to think about it, and because all the data science is completely mathematics or statistics or your artificial intelligence and all that. So today what I am going to present to you is just one very simple application of what you study in your graduation. Okay, so that is what I am going to present to you, and it's just a very simple application of the known concepts that all of you are familiar with. Okay, so that is I hope all of you can see the screen, More sir.
Yes, sir. It is now going to visible, sir.
Yeah. So can you see the screen?
Yes. I request to student, please pin the screen so that you can see the PPT. And I request to resource person Malekar sir.
Okay.
You should go through. You should use two languages, English language as well as Marathi so that it will be compatible to all students.
Okay. I'll try to do that. मी प्रयत्न करेन. ओके. तर मोरे सर ही सगळी मुलं कुठली बीएससी मॅथमॅटिक्स म्हणजे मॅथमॅटिक्स बॅकग्राऊंड आहे त्यांना, राईट? अँड त्यांना थोडं फुरियर ट्रान्सफॉर्म माहिती आहे. ओके.
टीवायच्या स्टुडंटला माहिती आहे फुरियर ट्रान्सफॉर्मचा पेपरच होता एक सेपरेट इंटिग्रल ट्रान्सफॉर्म. फक्त FY माहित नाही.
आय थिंक वी हार्डली नीड मच ऍक्च्युली. वॉट आपल्याला पाहिजे ते फक्त थोडंसं कॉम्प्लेक्स नंबर्स एव्हरीबडी नोज, राईट?
येस सर.
ओके. सो वी आर गोइंग टू यूज लिटिल बिट ऑफ कॉम्प्लेक्स नंबर्स. आणि मॅट्रिक्स सगळेजण स्टडी करतात, 11वी-12वी स्टडी करतात, राईट? मॅट्रिक्स थिअरी. So what is this fast Fourier transform? I think those who are studying Fourier transform, they are aware of this. But Fourier transform is used in a continuous word. Continuous word in the sense when you have a continuous functions. Okay. But when you go to a discrete case, then this Fourier transform has to change. So what is the corresponding thing that one is interested in? Okay. So that is what is of much interest, I think, to the practical world, to compute this Fourier transform in a finite or in a discrete case. Okay, and that is what is called as a discrete Fourier transform. And ते जेव्हा डिस्क्रीट फुरियर ट्रान्सफॉर्म कम्प्युटर मध्ये कॅल्क्युलेट करायचा असतो, तर कम्प्युटेशनल जो टाइम असतो, that time you want to reduce the time of the computational time of this discrete Fourier transform. You want to reduce, and that is why this fast Fourier transform has come into picture. Okay. So this algorithm is very simple application of your linear algebra. Okay, means very basic matrix theory you need. थोडंसं कॉम्प्लेक्स नंबर्स बद्दल माहिती पाहिजे. आणि हे सिंपल आयडियाज यूज करून हा अल्गोरिदम, यू विल सरप्राइज दॅट दिस अल्गोरिदम हॅज मीन्स इट्स कॉल्ड एज एन अल्गोरिदम ऑफ सेंचुरी इन अ वे व्हेन इट वॉज इनिशियली इन्व्हेंटेड. अँड only thing is that that time when it was invented, the computer was new and all that, and they wanted to reduce the time of this calculation. So this Pune and Tukey was the first person who came with this algorithm, and what I am going to discuss with you is this Pune-Tukey version of this Fourier transform, which is actually you want to compute this in a finite case in a faster way, because computational matter, if you see, then normal evaluation will take a lot of time, whereas this algorithm will reduce your number of computations. Okay. So to start with, I'll just tell you about the Fourier transform, what it is. Fourier transform is the integral of the function fx over minus infinity to infinity e raised to power minus I omega x dx. This is called as a Fourier transform f of omega. Okay, and it's basically an integral, and this Fourier transform itself has a lot of applications in signal processing and all that, and those who are little bit familiar with the electronics and all that, they'll understand how much is important this normal Fourier transform which we study. I think the problem that we have is we don't see the applications when we study mathematics, so therefore we don't realize the importance of that. But if you ask any engineering resource person or engineering research person, he will tell you you cannot do research in engineering without mathematics. So mathematics is the core. Okay. Only thing is we are not aware of that, or we probably don't teach in that way. Anyway, this is the Fourier transform, and then similarly you can just define the inverse Fourier transform. So inverse Fourier transform is just the inverse of this with this 1 over 2 pi factor, integral minus infinity to infinity, and this exponential becomes e raised to power I omega x. I think all of them are aware of this e raised to power I theta.
Yes, sir.
This is your 12 standard stuff, right? E raised to I theta is cos theta plus I sin theta. Okay. So this is the inverse Fourier transform, and then this is a Fourier transform. And then there are various other transform that we study. I think we are not going to go into details of that. Laplace transform, then and that things are there. Okay. And there are some properties of Fourier transform that also probably some of the, I think, last year students probably are aware of that. I am not going to spend much time on that because I am going to go to this algorithm, that is fast Fourier transform algorithm. Okay. So there are some properties of Fourier transform that some of you, I think I must say something about this, that when you talk about Fourier transform, this affects, you can thought of as a signal or an input data. Okay, and then this Fourier transform of that signal f of omega is a spectrum. Now I am going little bit off the mathematics, but because since we want to talk little bit of application, so I must refer to application. Okay, so you can just look at little bit of this because all these are very frequently used in signal processing and all that. Okay. So this is your usual Fourier transform. Then you have some, I think many of you do. I am not going to do this example and all that. This is just a calculation. Okay. Then you have some Fourier transform properties, that this Fourier transform is periodic, and then what happens to the scaling factor and all that. Okay. So that all theory one can read and study. Then this convolution theorem, that Fourier transform of a convolution. Convolution is by the way, is a very important aspect in studies of a Fourier transform. Okay, convolution of two signals. When you take a Fourier transform, it is the product of their Fourier transform. And then Fourier transform of delta function and all that. Okay, so this is all the theory which goes in a continuous case. So now we come to a discrete case, that is the discrete Fourier transform. So this is probably many of you might not be aware of, but it's very simple idea. So when you come from a continuous case to a discrete case, and your input is a signal, and that signal can be considered as a set of n coordinates, like in 2 dimension we represent any coordinate as x and y, right? So in n dimension, or if you have an n vector, we can represent it as a vector an with the component a0, a1, a2 up to an minus 1. And this is generally coming from, this needs to be a periodic. So after this n minus 1, then you are going to repeat it. So it is modulo n. Okay. So an is an plus jn for all n and j. Okay. So the discrete Fourier transform is applied on this discrete vector or a finite sequence of a vector. So what is the analogy? Analogy, when you go to a discrete from continuous, that integral is represented by a sum now. So it becomes a sum. Okay. And these exponentials which are there in your usual continuous Fourier transform are still there, but now they becomes the nth roots of unity. I think all of you know nth roots of unity, very important concept in mathematics. I think they study cube root of unity, right? What is the property of nth root of unity? I think More sir?
Yes, sir.
They know nth roots of unity? Right?
For a SOI student, it is known, but for FY, it is not known.
Okay, so nth root is like cube root. So upon cube root of unity, cube root of unity is some
like that.
You have 1 omega square. And what is the property of this nth roots of unity? Their sum is 0. Like 1 plus omega square, I think is 0. Right? So that is cube root of unity, and then the same thing you extend it to nth roots of unity. So that becomes this exponential 2 pi I k n by n. Okay, so this is the nth roots of unity, a very important concept, and with a lot of places one uses this. So that is applied on this vector an. So that is what is discrete Fourier transform. Very simple. Okay, this exponentials, this integral becomes sum, then those function becomes the vector, because you are in a finite world, you are in a finite sequence, and those exponentials are still there, but now they become a nth roots of unity, a version of those exponential. Okay, so when you apply this, that is what gives you the discrete Fourier transform. So if you apply it on an n sequence of vector, you get output as a n vector ak. Okay, so more commonly you write this as nth root of unity as wn, which is e raised to power minus 2 pi I by n. Okay, that is your nth root of unity. And so we can represent the same thing in terms of these w's, because this is what we are going to use, and it is easy to denote in the notation also. So wn raised to kn, n going from 0 to n minus 1. So these are called as the nth roots of unity, and you know that when you raise it to the nth power, you get 1. Okay, and then what is good thing about this? I think based all of you are studying groups. So if you take the set of nth roots of unity, they form a
Groups.
finite abelian group, right? Under what operation?
Composition.
Under operation of multiplication. Okay, and what happens when you multiply these two nth roots of unity? It is basically you have to just add the indices. Means you have to just add the power, and that is modulo n. Okay, so there is one nice way to represent this in terms of unit circle. Okay, for example, when you take n equal to 2, so when you put n equal to 2 here, what you get is the square root of unity, right? Square root of unity is just 1, and so w2 0 is 1, that is the base power, and w2 1. When you put n equal to 2, you get e raised to power minus pi I. So that is cos pi plus I sin pi. So sin pi is 0 and cos pi is minus 1. So this becomes a minus 1. So this is 1 and minus 1. So these are the two roots of unity which you can represent a vertices of regular polygon inscribed in a unit circle. Okay, so you can represent them in a unit circle, right? Then similarly for n equal to 4, so these are the four roots of unity: 1, I, minus 1 and minus I. Okay, so they are the four corners of this polygon. Okay, and then 8 roots of unity. Okay, so there are 1 here, and then these are with you can calculate what are these 8 roots of unity. Okay, it's very easy calculation which one should do. Okay, so you can represent them again on this complex plane on a unit circle. Okay, so and since the nth roots are points on a complex unit circle, so when you multiply this is equivalent to rotation clockwise by this angle. That is what you can see when you multiply these two numbers. What you get is just a rotation. Okay, you will get a next number, right? Means you just rotate. Okay, so raising this nth power of this nth roots of unity is actually just modulo n. Okay, means after modulo n it will repeat. Means, see for example, I am looking at n equal to 4 case. So I know there are only 4 roots of unity. Now if I raise it to the power more than 4, then what is going to happen? You will get repetition of the same numbers. Okay, it is one of those things only. So that is why it is modulo n. Everything is modulo n. So when you apply the discrete Fourier transform on this vector an, you get a vector ak, and which is also of the same size. Okay. So once you have this definition of discrete Fourier transform, you can similarly define what is inverse discrete Fourier transform. So inverse will change the rule. Okay, so this will become w minus kn of ak, and then this is one normalization factor 1 over n, and you will get back to a an. So what is the good thing about this Fourier and discrete Fourier transform is that they hardly change. Means your input data you just transform into another type of data. Okay, and then you can get back to original data by reverting that. That is a good part of it. Okay, so this is what they are saying, that formula is identical except the roles have been exchanged. Okay, and you get a 1 more. So always this is a one thing that one should always look at when you are studying something new, and then you should study the examples. Okay, and the same thing we do here. We have defined it for general n. Now you just want to see what it is for some particular value of n. What is this discrete Fourier transform? Okay, so for n equal to 2, you first look at what is your root of unity. So this is e raised to power minus 2 pi I by 2. So that 2 gets cancelled, you get e raised to power minus pi I, which is cos pi plus I sin pi. But cos pi is minus 1 and sin pi is 0. So you get minus 1. So your discrete Fourier transform becomes this W2 is minus 1. Let me just go back to the definition. This is minus 1. And then you raise to Kn. This is raised to Kn and An. And n runs from 0 to 1. So you give a value to n. So that is A0 and A1. This is minus 1 raised to K0, n is 0 and K1. So when you put this is what you get a general term. Ak is equal to this. So this is when you put k equal to 0, you get A0 as A0 plus A1, and k equal to 1, you get A0 minus A1. So this is what very simple terms. हे जर आपण थोडंसं एक्सप्लेन करायचं म्हटलं तर यू कॅन रिप्रेझेंट दिस एज अ मॅट्रिक्स. मॅट्रिक्स फॉर्म मध्ये कसं दिसेल हे बघूया. लेट मी जस्ट डू दिस. So this is, I'm not good at this, but let us see. So this is your A0. Okay. This is A1 row. And here basically these are all matrices. This discrete Fourier transform is nothing but just a matrix of nth roots of unity. 1, 1, 1. This is minus 1, a matrix, and then you have this right hand side A0, A1. Okay, so what does it means is that this matrix just transform this vector A0 A1 into a new set of vectors. That is what is n equal to 2 means. Okay, so this is nothing but just a matrix of nth roots of unity. So this is for n equal to 2. Okay, and you can similarly try doing it for n equal to 3 and 4 and so on. So let us look at 4 case also. So what is the fourth root of unity? You are putting n equal to 4. So e raised to power minus 2 pi I by n. So that n becomes 4. So that is minus pi I by 2. So that is cos pi by 2 minus I sin pi by 2. So cos phi by 2 is 0, and you get this as minus I. So this minus 1 is replaced by minus I raised to kn, running from 0 to 3 and an. So you give values to n, so you get this linear combination, a naught raised to minus I raised to k, minus I raised to 2k, minus I raised to 3k, and this up to 3k. And then minus I square is nothing but minus 1. Okay, and that is what you get, a general vector ak. And then you give values to k to get all these coordinates. So what does it looks like?
Hello.
It looks like this. Okay, for k equal to 0, all these indices is 0. So we just get a0 plus a1 plus a2 plus a3. K equal to 1, you will get the second row. K equal to 2, you will get third row. K equal to 3, you will get fourth row. And then this whole thing is, you can represent it as a matrix form in this way. Okay, 1 1 1 in the first row, then this is your input vector. Okay, then the second row coefficients 1 minus I minus 1 I, then 1 minus 1 1 minus 1, third row, last row is 1 I minus 1 minus I, आणि त्याच्यावर हा वेक्टर अप्लाय केला आहे. So that result is this vector on the left side. तर याच्यावरून काय दिसतं आपल्याला की this discrete Fourier transform is basically a matrix of this nth roots of unity which transforms the unit vectors in certain way and gives you a new set of vectors. So the question is basically in this algorithm which I am trying to talk to you is, now we are looking at very small cases, that is we are just looking at n equal to 2 and 4. The matrix is very small, so there is not much problem. But when you go a very large size of matrix, let us say we are looking at n equal to 100, so that is n 100 by 100 matrix, and you want to compute this and you want to do it faster in computer. So that is going to take 100 by 100 multiplication and add. So that is how much time it is going to take. So that is going to be, for example, if you look at this 4 by 4 case, and meanwhile these all A0, A1, A2, A3, they can be a complex numbers also. So you are adding complex numbers, then you are multiplying here. So in a way you are going to get 16 in 4 by 4 case, 16 types of addition and multiplication. And in 100 case you will get 100 square, and as your n is increases, this is going to be very time consuming, and that was what the question was, how to do it faster. Means this is what usually we do in mathematics, that you just separate it like this, but in computational world you want to play with it and then you simplify your calculations or you reduce the time of this in computer. Okay, so the one thing that was thought of is that you just reshuffle this indices here of the input vector. So you take even indices first, so that is A0 plus A2, and then these are the odd indices. So you just regroup. The same thing I am just regrouping. And what I am going to do is that I am going to do these additions first. Okay. So for A0, I am just putting a bracket. So I am going to do this. Now for A1, again I am going to take these real parts here. So again A0 and A2, and imaginary parts separate केलाय. त्याच्यामध्ये odd indices आहेत. So even indices आणि odd indices असं सेपरेट केलंय आपण. ठीक आहे, प्रत्येक मध्ये A1 मध्ये केलंय, परत A2 मध्ये केलंय, आणि तसंच सेम A3 मध्ये केलंय. ओके, अँड सो दिस सेव्स लॉट ऑफ ऍड्स. याच्यामुळे काय होतं की हे कॅल्क्युलेशन तुम्ही करता, अँड हे तुमचे जे ऍड आहेत ते तुमचं बरंच कॅल्क्युलेशन सेव्ह करतात. ओके, आणि हे तुम्ही आधी कॅल्क्युलेट करून घेता. इन्स्टेड ऑफ डुईंग इन दिस ऍक्च्युअल मल्टिप्लिकेशन यू डू दिस कॅल्क्युलेशन फर्स्ट. ओके, आणि मॅट्रिक्स कॉम्प्युटरमध्ये ते तुम्ही स्टोअर करू शकता आणि तुम्ही रिकॉल करू शकता. आय थिंक कॉम्प्युटर लँग्वेज वगैरे केल्यात त्यांना कळत असेल. अँड हे कॅल्क्युलेट करून नंतर तुम्ही कॉम्प्लेक्स मल्टिप्लिकेशन पण करताय. ठीक आहे ना. सो हे जर आपण डायग्रामॅटिकली रिप्रेझेंट करायचं म्हटलं तर व्हॉट आर वी डुईंग. सो आपण हा डायग्राम फॉलो करतोय. हे दोन पी अँड क्यू नंबर्स आहेत. दे कॅन बी एनी वन ऑफ दिस A0 A2. So and then alpha is this complex multiplier which is I in this case. तर आपण काय करतोय, या अल्फा आणि क्यू ला मल्टिप्लाय करतोय आणि देन वी आर ऍडिंग दिस टू पी प्लस अल्फा. ओके, सो दिस इज व्हॉट वी आर डुईंग. ऍक्च्युली इथे आपण तेच करतोय. बघा इथे हे दोघांची ऍडिशन केली आहे. इथे A0 मायनस A2 हे केलंय आणि हे कॉम्प्लेक्सने मल्टिप्लाय केलंय आणि त्या पुढच्या नंबरला त्याला मल्टिप्लाय केलंय. सो दॅट इज व्हॉट वी आर डुईंग इन इच केस, इन एव्हरी 2 बिट्स. प्रत्येक केसमध्ये आपण करतोय आणि प्रत्येक ह्याच्यामध्ये तो कॉम्प्लेक्स अल्फा मे नॉट बी कॉम्प्लेक्स, इट कॅन बी रिअल ऑल्सो. लाईक हिअर इट इज रिअल, हिअर इट इज कॉम्प्लेक्स, रिअल अँड कॉम्प्लेक्स. सो वॉट एव्हर इट इज, यू जस्ट फॉलो दिस पॅटर्न. ओके, सो इफ यू लुक ॲट दिस डायग्रामॅटिकली व्हॉट यू आर डुईंग, हे आपण असं रिप्रेझेंट करू शकतो. वरती जे आपण कॅल्क्युलेशन सेपरेट केलेलं आहे, तर हे आपण काय केलं, हे जे आपला हा इनपुट वेक्टर आहे त्याला आपण रिशफल केलंय. सो दिस इज A0 and A2 and then this is odd indices A1 and A3. आणि पहिल्या केसमध्ये आपण ला जो मल्टिप्लायर आहे तो रिअल आहे, सो दॅट इज 1. सो A0 प्लस A2. आणि सेकंड केसमध्ये तो -1 आहे, सो यू गेट A0 मायनस A2. So that is what you are doing. Here you get A0 plus A2 and A0 minus A2. That is what you are doing there. Same thing you are doing with odd indices A1 plus A3 and A1 minus A3. Okay. Now here je ahe, this thing you have to relate to your original vector. So how do you get your original vector from this? Now this A0 and A2 will give you capital A0 and that is related to A1 plus A3 coming from here. So that is what is A0, right? So here it also हाच जो डायग्राम है, this is actually called as butterflies. They looks like a butterfly that you extend to the next stage. So this is going to here and this one goes here. So this is 1. So you will get A0. So A0 plus A2, A1 plus A3. Now how do you get this is A1. A1 is A0 minus A2 from here and then minus I from here, A1 minus A3. So that is going to give you A1. And then how do you get A2? A1 plus A3 from here and then A0 and A2 coming here. Okay. So that is A3 and A3 is A0 minus A2 from here and I times A1 minus A3. So that is it. So this whole thing that you are doing here can be represented in terms of this diagram. And these are called as butterflies. Very well known name for this. They looks like a butterfly. So at each stage, the pehla the butterfly that is of size 2 and then you increase that size to 4 in this second butterfly. आणि या सिक्वेन्सनी जर तुम्ही गेला की यू विल गेट युअर वेक्टर. ओके, तर इथे तुम्ही बघितलं की ही जी कॅल्क्युलेशन आहे तुम्ही एकदाच करताय आणि तेच कॅल्क्युलेशन परत वापरताय. सो हे प्रत्येक स्टेजला तुम्हाला करावं लागत नाही. दॅट इज द ऍडव्हान्टेज ऑफ दिस. आणि हे सेम थिंग यू कॅन ट्राय टू अंडरस्टँड दिस फॉर हायर व्हॅल्यूज ऑफ एन. याच्यामध्ये तुम्हाला एक नोटीस, you might notice one thing is that I am just taking all even powers of n. Okay, so I think I'll just explain you n equal to 8. Okay, so n equal to 8 we'll see, then you can try to figure out what is n equal to 16 from that. Okay, so the effect is a fast algorithm for computing DFT. If you take 2-point DFT and a 4-point DFT, then you can generalize it to 8-point, 16-point. So this first algorithm which was derived is derived for even powers, that is powers of 2. Okay, that was the first thing that was derived, so that was by Pune-2K algorithm. Okay, so to compute DFT of n point sequence, तो तुमचा जो input vector है, you would generally अपन जो normal केलं तर ते तुम्हाला n square multiplication, order of n square multiplication and add you will have to do. But whereas if you use the FFT algorithm, then you require order of n log n multiplies and adds. Okay, so that is a good thing about this reduces your calculation computational time quite a lot. And these computational algorithms are tremendous demand nowadays. Means basically all the algorithm that generally you do a Google search, right? So that Google search is also, there is an algorithm which actually that gives you a best result what you want. So there is some algorithm, and that algorithm is nothing but mathematics. Okay, so the prerequisite is that one needs to be patient to go to that particular. Okay, so obviously we are just looking at a initial case which is easy to understand, and this is called as dissemination in time FFT algorithm, whose length is power of 2. Okay, so I think I'll discuss this 8-point FFT also. I think let us look at how does it look like. So 8-point FFT is you're looking at W8, which is becomes your 8th root of unity is this e raised to power minus pi by 4, that is 1 minus I over root 2. And if you look at the diagram, it goes like this. Okay, so this is one more extension of what you have seen. So look at that, those doubles here, they are still here. So these are your doubles. Okay, and they become 4 at the next stage. And here you will find they are grouping in 4 groups, and in the last stage it goes to a general case which is 8. So let us just understand this. I think what has been done here. Okay, so like in this case you have even terms group there. There is one more thing that is done here now. This is your input sequence is A0, A1, A2, A3, A4 up to A7. So these are the even sequence here, and in the even sequence also, if you look at, you don't have A2 after that, it is A0 and A4 grouped together, A2 and A6. Okay, then this odd sequence A1 and A5 and A3 and A7. So as usual, this 2 by 2 DFT goes here. Okay, A0 or 2 by 2 case is this much only, A0 plus A4, and this gives you A0 minus A4, and then this goes here, which is your W2, which is the square of your primitive nth root of unity, that is multiplied here. Okay, and this goes here, then 6 power here. Then obviously question is, how do you know this and how do you understand this? It's not that difficult. Okay, but these figures are nice to understand. Like suppose I want to get A0, so you go along this A0, then A4, go here, and here you meet this W0. W0 is just the 0th root of unity, so that comes from here. So A2 and then A6, that goes here, and that goes ahead, and that will meet to this A3 and A7. So that is going here. That is what is going to give me. So this is again going to be some matrix like this. Okay, I think I must show you that matrix. Yeah, this is the matrix. This is the case, your usual input sequence. This is your discrete nth roots of unity matrix, W0. This is the 0th row, this is the first row, second row, third row, fourth row, and in the same row you just see that this will have those multiply 2, okay, W3 6, W4 8 and all that, okay. So this is what is this multiplication in FFT algorithm is explained here, okay. So for example, I want to get the first row. So first row is going to be what? This is all 1. W raised to 0 means it is 1. So it is just addition of all this. A0, A1, A2, A3, A4, A5, A6, A7. That will give me capital A. So let us see how it is done here. So from here I am going to get A0, A4. Okay. That is going here. And then you are meeting here this A2, A6 with 1 here and meeting here. Okay. And from next you are going to get this W0 from here, which will bring these two together, A3, A7, which will group here with A1, A5, okay. And so that way you will get all these suffixes and they will go to here to give you A0. So hold this multiplication in FFT algorithm you can understand from that diagram. Okay, I think one can see what it is for each of the case. One can actually multiply and check. Okay, but what one has to see, there are two things that one has to understand here. One is that this reshuffling of the indices input vector here on the left side, and at the first stage these roots of unity, they are just 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. So this corresponds to the DFT of a size 2. So one butterfly is a DFT of size 2 at each stage. Okay. Now you cross over and go to the next stage. You come to the n equal to 4. So that next stage you get, for example, if you are just in the even sequences, there you get this 4th roots of unity. So there is a butterfly corresponding to the 4th roots of unity. One with the even suffixes, one with the odd suffixes. And then these two butterfly merge here at the final stage. Okay, to get you the actual output. Okay, so these calculations you have to do only once here. Whereas in normal multiplication of matrix, you have to repeat that at every stage. That is a good point of this. Okay. So I think it's a good exercise to understand this, what this is. It is actually the effective algorithm. Okay. So that's what they are saying here. So these are called as butterflies, and each butterfly takes two complex numbers, computes from them to another complex numbers, p plus alpha q, p minus alpha q, where alpha is a complex number, so you can represent it in the form of the butterfly operation. Okay, so let us try to understand what this order is. So in the diagram of 8-point FFT, note that the inputs are not in normal order. So this is your normal order input, A0, A1, A2, A3, A4, A5, A6, A7. Now whereas you are inputting them in this order, A0, A4, A2, A6, A1, A5. So why it is so? So the reason is, you just look at this table. So this is the index input sequence nj. So this is your initial input, say, and we are just looking at the index. So initially it is in serial order 0, 1, 2, 3, 4, 5, 6, 7. Now in the reshuffled order, our input sequence is 0, 4, 2, 6, and here it is 1, 5, 3, 7. Right? This is what our input. Now if you look at the binary representation, I think all of you do some binary number. Every number can be expressed in terms of binary decimals. I think
Yes,
that
sir.
is right.
Yes.
So these are binary representation of these indices. So if you look at the binary represent of J index, is given by this 0, 1 is this, then 2 representation is 0, 1, 0, 3 representation is this, 4 representation, 5 representation, and so on. Then look at the binary representations of this reshuffled order, that is second row, that is written here. So 4 binary representation is 1, 0, 0, 2 is 0, 1, 0, 6 is 1, 1, 0, 0. So 1, 0, 0 becomes 0, 0, 1. 1, 0, 1 is this, 1, 1, 0, 0, 1, 1, and this is it. So what you notice here, yes, anything you observe here in these two representation? The thing to observe is that this second row is just a reverse, bit reversal, that is called as a bit reversal, that is the word used here. So like here it is 0, 0, 1 and it becomes 1, 0, 0. 0, 1, 0 will remain same, here it is 0, 1, 1, it becomes 1, 1, 0. So it's a reverse order bit, right? 1, 0, 0 becomes 0, 0, 1. 1, 0, 1 is same, 1, 1, 0 becomes 0, 1, 1 and so on. So you rewrite this indices in such a way that they are in a bit reverse order. Okay, so this is what it's, the pattern is obvious. If J and Nj are written in binary, observe that each Nj is bit reversal of J. Okay, so this is part of sort of, I think some of you are studying graph theory and all that, you can say that your breadth first traversal of binary tree. Okay, so this sort of this is what we do, I think, in binary tree. So this rearrangement is just a bit reversal which simplifies your calculation. So it turns out that this FFT algorithm simply, if input array is rearranged in the bit reverse order, the rearrangement can be done in one pass through any array A. So how does you do this in the, this is what you do generally in the language, right? You have some for loop, so you input a number for j equal to 0, you get a nj. So what is j? You input j, that is your indices, your normal sequence. And what do you do in nj? You bit reverse j, that is nj. Okay, and you do this till the time, since j is less than nj, you just have to swap this, and then you get a reorder your sequence. That is what your for loop is. Okay, in computation, I think some of you do little bit of programming, so it's just an indication of that. And what is being done here, that you can understand, everything is discussed. Why do you get these numbers here? So because there is some sequence here, no? You are not putting them in any order. Why are you getting only this sequence? Okay, I don't have much time, so I think this is the one thing that one should understand, this, what is being done, why these indices comes here, 0, 2, 4, 6, and why do you get, these are real numbers here. I think that explanation is given here. You can go through this and understand. I think I will just go through this matrix multiplication, which actually tells you why the way of multiplying this is easier and very simple. Okay, that I'll just use a matrix multiplication. So this is your usual FFT of order 8. Okay, means this is your input sequence. This is your 8 roots of unity, 8 terms of matrices. This is your output. Now what we do in FFT, we reshuffle these indices. So A0, A4, A2, A6, A1, A5, A6. This is what we want to calculate. But when you do this reshuffling, then this your matrix is also going to reshuffle. And how do you do that reshuffling? The same way, like here you are interchanging A0 and A4. So exactly in the same way, you interchange your 0th row with the 4th row here. I'll just explain you this interchange, one interchange, rest you can understand. See, the 4th row here is starts with 4, W0, 4, 4, 0, 4, 0, 4, 0, 4. So that becomes now second column here. Look at this. This A2 indices is same, so that is left untouched here. 0 to 4, 6. You can see here. 0 to 4, 6, 0 to 4, 6. Then A1, this A6 replaces A3. So that is 6th suffix. So that is 6th column here. You will bring to the 3rd place. That is this place. So this is what is done here in this rearrangement of multiplication and these suffixes. And if you decompose this, so to start with, we get this smaller DFTs of 2 by 2. So W0 and this W4, so W0, W4. So these are your smaller 2 by 2 DFTs that you are operating here. This is your this stage. 1 minus 1, 1 minus 1 and so on. This is what is your first matrix. Yeah. Then this is your second matrix. 0 to 4, 6. Look at here. 0 to 4, 6. Okay. 0 to 4, 6. And this is your last matrix. So the same matrix is being broken into 3 multipliers with lots of 0. All these are 0. Wherever there is no entry, this dot means 0. So this multiplication is very easy. You are saving lot many multiplications here. Okay. So these are sparse matrices. So multiplying by bends on top is more expensive than multiplying by 3 sparse matrices on the bottom. So you have a lot of zeros, so that is very easy to do. And this is what is actually matrix form of this FFT that you are doing here. Yes. The same diagram which is here, you can represent it in the matrices form like this. Okay. And obviously this multiplication is much more easier. This is 8 by 8 you are doing, but you can think of when your n becomes large, like it becomes